Hi, welcome to section 7.3. We're going to talk about sampling and predictions and simulations today. So we're going to start by talking about samples and populations and how they relate to each other in terms of statistics. So when we want to gain a piece of information or maybe several pieces of information about a group of people, oftentimes it's not realistic to survey or collect that data on every single person or object in that population. So say for instance, I like to know the average student loan debt of the students that go to Washtenaw. Washtenaw Community College has a lot of students, thousands of students, so it might not be realistic to find that information out for everybody. I mean, I could ask maybe in a survey, but I know not everybody is going to respond. So instead of, figuring that information out from the whole entire population, so population refers to everyone at WCC, I might take a sample. So a sample might be, I could survey my class. Not a great sample. There's some bias there, and we'll talk about what that means in a minute. But I might survey, incoming freshmen, or maybe I send out a random survey to just, a random group of students on the campus, and hopefully most of them respond, and that's acts as my sample that's hopefully represents the entire population. So a sample is a collection of people or objects chosen to represent the larger collection. So the sample is the smaller group, and the population is the entire group. So for example, the entire WCC student body might be my population, and maybe I survey my class, and that would be the sample. Now, we can't talk about sample and population without mentioning bias. So bias is just prejudice in favor against one thing, person, or group compared with another. Usually it's considered unfair. So in the example I gave, if I survey my class and with the intention of it being representative of the whole WCC population, there's going to be some bias there, because if I survey my class of future education students like Math 148 or Math 149, I'm only surveying people that want to be teachers. They're attending school in a specific program. They're probably going to similar schools, so maybe a lot of them transfer to Eastern, and so they're going to have similar debt that might not be representative of the whole population, because we have nursing students and welding students and auto body and pre-med and all kinds of different programs. Oftentimes in my classes, I have a different proportion of men and women. In my class, it's not representative of the college. You want to look at those things like race, background, gender, and what people are studying, and there's all kinds of different variables to consider. So that would definitely be a biased sample if I surveyed my class. One good way of collecting a sample that is representative, or hopefully is representative, is to collect what's called a random sample. And if you look, we'll get to example 1 in a second, but if you scroll down here, you can see I have random sample there. It's the gold standard of sampling, and basically what that means is that you use some sort of random number generator to randomly select people in the population. So using my WCC example, what I could do is I could, assign every single student at the college a number, and the easiest way to do that would be to alphabetize the students, if I had one student list, and then assign each one of those students a number, and then I use a random number generator, and that number generator will tell me what number students I should select. So maybe I want a sample of 50. Well, it can give me 50 random numbers. I pull out those 50, I send them a survey, and hopefully they respond, and that hopefully is representative of the population. So That's one example of how you could do a random sample. So let's talk about example one. So, and this would be a great place to pause the video and see if you could do this one on your own. So a college professor is up for promotion. Teaching performance, as judged through student evaluations, is a significant factor in the decision. The professor is asked to choose one of his classes for student evaluations. The day of the evaluations, he passes out questionnaires and then remains in the room to answer any questions about the form filling it out. A, what is the population being studied? So again, hopefully you had a chance to think about this first. Pause the video. The population that he's trying to study here is all of his students. Well, and I shouldn't say he's trying to study, it's probably the college that he works for is trying to study all of his students. So, and then the sample that's being observed is the class that he's surveying. So I'm going to say the one class, and it says right here, choose one class he surveys. And if he's choosing right there, I'm thinking right away to that next question, bias. If the instructor himself is choosing the class, there's bias right there because he's making that decision. And you never know, like maybe he has students in that class that he knows he has a good relationship with. So that alone might, cause bias there. So he's choosing, so teacher chooses. Okay. The other thing that creates bias is he's in the room. I'm sure that can make students nervous. I remember when I was in college, we used to do teacher evaluations and we would just handwrite all of the evaluations. And I think back, and that, has a source of bias there because that, the teacher's been grading your work the whole semester. He or she probably might possibly be able to recognize your handwriting. And so there's lots of little details there to think about when you're collecting samples. And most of the time, they're never perfect, but these are things just to consider. So like I mentioned before, random sampling is the gold standard. So think of like a lottery. So let's go through a couple of examples and think about if there's randomness to these or not. And this would be a great place to pause the video and try these on your own first. So A, WCC employees surveyed by assigning a random number to each person, and then certain numbers are called for their opinion. I would definitely say that's a random sample because we're using a random number generator. B, class of 30, I select the student sitting in the first row. I would definitely say not random because I'm selecting. And I'm only selecting the people in the front row. I'm not using a random number generator. C, I play the lottery. I can pick any number from 1 to 1,000,000. One number will be picked out of a drum. I select numbers 1, 2, 3, 4, 5, and 6. Is my sample random? So this is where, you have to think about if I'm selecting the numbers, and I'm choosing to select those numbers, then it's not random because I'm choosing. But what I will say, this is an interesting one to think about. I've asked before in terms of probability. It's just an interesting question. If I choose lotto numbers 1, 2, 3, 4, 5, and 6, I always like to ask students, do I have a good chance of winning? And a lot of times students will say, well, no, that's a horrible choice. Like you should randomly choose numbers. Like those are all low numbers. But statistically speaking, you have the same probability of winning by picking 1, 2, 3, 4, 5, and 6 than any other combination of numbers because they each have an even chance of getting picked. But if I'm selecting, it's still not a random choice. And then D, the pollster wants to estimate Democrats in a town, goes to a local mall to poll 100 people. So there's not a ton of information here. It doesn't say whether or not this person assigns random numbers to people. My guess is they don't if somebody's going to the mall. So I'm going to say it's not random because there's not enough information. But just even if the person used a random number generator at the mall, which would be great, they're still going to the mall. So they're going to the local mall. I never go to the mall. So there are people that never go to the mall, and there are people that, go to the mall all the time. So it's not it's a specific place that this poller is choosing. And the mall might not represent the whole population. So I'm just going to say mall doesn't represent the entire population. Now, it could do a decent job. This isn't saying, you know, that every poll that's conducted at a mall is horrible, but it's not entirely random. So if I were in class, what I would do is I do a little activity using a random number generator, and I'm not going to go through the whole thing right now, but I do want to show you a little bit of how it would work and give you an idea of what I mean when I say random number generator, because sometimes people will hear that and they'll be like, well, what exactly does that mean? So you can Google random number generator, and there's all kinds of websites out there that will really quickly create a random number for you. I'm going to use the graphing calculator just because it's a handy tool and I have it on the computer. If you have a graphing calculator and you're just curious, it's under the math window and then the probability menu. And any of these menu options that have rand in them, these are all random number generators. I'm going to select random int, stands for random integer, because I only want integers, which are numbers, positive and negative whole numbers. So what I would do if we were in class is I would, let's say I have 30 students, I would go around the room and I'd assign a number to every student. So this part isn't random. I just start at one end and I'd assign in order 1 through, let's say 1 through 30. And then what I do is I'd come here and I'd say, okay, I want some numbers 1 through 30. And I'm first going to ask the calculator to give me 5 numbers. Okay. And so what I would do at this point is I would ask every single person in the class, I'd say, you know, think about how many keys you have on your, like in possession right now, and they could look. So every single person looks, for how many keys they have. And then what I would do is I would actually take the average of the entire class. So I'd spend, you know, a couple minutes and I'd ask every single person how many keys they have, and I'd find the actual average number of keys of the entire class. Then I would use this random number generator to give me 5 random numbers. And so the random numbers are 30, 9, 9, 4, and 2. And actually I've got a repeat there. So what I would do is I'd probably do that again. And I think there's a way to do it where you don't get a repeat. Oh, you know what? Yep, random int, no repeat. So we're going to go number 8. So we're going to say lower is 1, upper is 30, and then we want 5 numbers. And so it would give me 5 numbers. Okay, cool. So this time I don't have any repeats. And I would say, okay, person 22, how many keys do you have? Person 1, how many keys? Person 13, person 10, person 30. And I would take the average number of keys. And oftentimes that average, it's usually not the same as the average of the class. Like it's you know, not too far off, but it's not the same. And then I would do it again, only I'd pull 10 people and I'd say, and we'd see, okay, well, is the average closer to the real average when I pull 10 people? Is pulling 10 people better than 5? And then I'd pull 15. And oftentimes the more people that you sample, your results end up being closer to the actual results. It's actually called the law of large numbers. And it doesn't always work out that way, but most of the time it does. So that gives you some idea of how you could use a random number generator to generate a sample. So speaking of sampling, it's good to talk about one specific type of sample called a stratified sample. And this comes up a lot just in real life examples. And a stratified sample is when you have a population that's divided into certain groups. So this might be like, think of a high school, for example, has freshmen, sophomore, juniors, and seniors. That might be an example. Or maybe you have a group of people and you want to know their average blood pressure, and there's men and women in the group. So maybe you want to, though there's 2 groups there, or maybe different age groups within a population. And oftentimes when you're trying to find a sample, you want to try to find you want to take a proportionate number of people from each of those groups so that they're all represented. So take that high school example. Let's say I did a random sample and most of my sample were seniors. Well, even though it was random, I'm getting information from a lot of seniors, and I'm not getting information from the other groups. So we could use a random number generator to generate numbers specifically within each group to make sure that they're all being represented. So let's take a look at this example, and hopefully this will make a little more sense. So this would be a great place to pause and you could read the problem. So we've got a city council and they want to sample the opinion of the adult population of 80,000 people, okay, on how to on a plan to build a public swimming pool. So 80,000 people, I'm just going to jot down, that sounds like my population, because um, they that's the entire group that they want to take a that's the entire group that they're looking to find information about. And so the population is divided into 3 groups. So here's where the stratified comes in. We've got high, middle, and low income. They're only sampling 1,500 people. It's not manageable probably to survey 80,000. So 1,500 people is the sample. So sample is 1,500. If 16,000 people are low income, 56,000 are middle income, and 8,000 are high, determine the size of the sample for each group. So these are really big numbers here. These are way bigger than my sample number. So these numbers are talking about, these are the numbers in the whole population. So we have 16,000 people that are in the low income group out of the 80,000. So what we can do here is I'm going to come to low income since that's the first number that was given. And we can take 16,000, okay, and divide it by the total, 80,000, okay? So that's the number of low income people compared to the total of the population. And what we can do is we can divide those two numbers. We can get a decimal. In this case, it's 0.20, which is the same thing as 20%. So what this says is 20% of the population is low income in that category. And then let's keep going. So 56,000 are in the middle income category. So what we can do is do 56,000, and that's our middle income, divided by the total, which is 80,000. And if we divide those two numbers, we get 0.70. And as a percent, I don't know why I wrote 8, as a percentage, it's 70. So that's our decimal. So 70% are middle income. Now from there, you could look and say, oh, 70 plus 20 is 90, so the rest must be 10, but it doesn't hurt since we're given that number. I'm going to go ahead and just do 8,000 divided by 80,000 just so we can go ahead and complete this and make sure that it all works out. And it does. You divide those two numbers and you end up getting 0.10, which is 10%. So we get 10% are in high income, 70% middle, and 20% low. And so ideally, when we survey those 1,500 people, we want to get 10% of them as high from the high income group, 70% from the middle, and 20% from the low income group. And that way our sample will be somewhat representative of the population in terms of at least income. There are other, characteristics that you could also do a stratified sample for as well, but we're just looking at income. So to get the sample size, all we need to do is find the decimal, or the proportion, times the sample size, the total sample size. So we're going to take 10% times 1,500, and that equals 150 people. So we got 150 from the high, and then we're going to do the same thing here. So 0.70 times 1,500, and you end up getting 1,050. And then I'm going to take this decimal, 0.20 times 1,500, and you end up getting 300. And then just to double check, so we're just going to check by adding 150 plus 1,050 plus 300, all of those sample sizes, and we should get our sample size that we were told about in the problem, which we do. So that just allows us to check our work. Okay, so we're going to kind of switch gears a little bit here, and we're going to talk about distribution of data, and then we're going to talk about some normal distributions or the bell curve. So this distribution, there's a lot of different ways that we can display data, but if we're looking at data in terms of a graph, a lot of times you'll look at a graph and it's a good visual way of illustrating data being clustered together, but oftentimes, there's going to be some skewness that might be pretty obvious when you look at a graph. And so anytime you see a graph where there's a definite high point, like on the left here, so we've got a definite high point here, and then it tails off to the right. So I would say most of the data is on the left, and the least is on the right. There's really just a few that are on the right there. When this happens, we say that it's skewed to the right. And I know it seems weird because it's like, well, why is it skewed to the right when most of the bars, most of the data is on the left? That's where the high point is. Well, we say it's skewed to the right because most of it's on the left, and it's just these outliers over here that are making that are changing the graph and making it look like there's that tail there. Because if those outliers weren't there, we just have these bars on the left and that would be the graph. And it wouldn't look skewed at all. And so if you think about this, I'm sure you could think of a real life example. Think of an example of some sort of data that we might look at where most of the values are going to be small. And then there's very few that are on the right. I can think of one example off the top of my head here. It might be number of children. So maybe you survey a large group of people and you ask them how many kids they have, and maybe this is 0, 1, 2, and 3. So most people have anywhere from 0 to 3 kids. And over here on the right, these are people who have 8 kids, 10 kids. And so it's just showing that most people have a few number of kids, and then you have those couple of examples on the right there. And then just like you can have data that's skewed to the right, you can also have data that's skewed to the left. So I'll just draw kind of a curve there to show how this data is shaped. We've got most of the data on the right and least on the left. So these are our outliers. And I'll just, one example might be heights of basketball players. Heights of basketball. So we'll say NBA players actually. And so most of them are going to be tall. And I would say there's a few shorter players that are outliers, but most of them are going to be tall. So we say that's skewed to the left because those shorter players are skewing the data. And then a symmetric distribution is where we've got the mean and the median and mode, so those measures of average is just going to be kind of around the middle, and they're evenly distributed on the left and right. Now in reality, in real life, most real life scenarios, they're not exactly symmetric, but it could look somewhat symmetric, and as long as it's somewhat symmetric, we still call it a symmetric distribution. So one of the most common symmetric distributions that comes up quite a bit in real life and statisticians use all the time to draw conclusions of different things in our population is called the normal distribution. And the normal distribution is just, you may have heard of this referred to as the bell curve. So anytime you see data where there's a curve to it, and it might be, like a bar graph over here on the left, you've got some chunky bars, but if, there's a general curve to the data like this, where there's most of it's in the middle, and then there's a fewer amount on the left and right, then we say it's a normal distribution. There's a lot of different real life examples that are normally distributed. For example, IQ test. Most people score in the middle, and then we have a few people that score really high, a few people score really low. Heights for male and females are normally distributed. So there's the average height in the middle. Most people are pretty close to average. And then we have, the outliers that are on the right and left. And there's many other examples as well. So when data is normally distributed, the nice thing about this is we have some conclusions that we can draw just from the shape of that graph, and we can take these conclusions and apply them for any scenario that's normally distributed. And so this graph right here, this is a picture that you're probably going to want to just copy down on your paper. And I think you can, these labels on the x-axis, this is directly from your book. These look a little bit confusing. What you can do here is just write in the very center where you see the X bar, that's your mean. So in the very center is your mean, and where you see this X bar plus 1 sigma, all that means, and I'm just going to write it up here, this is 1 standard deviation above, I'm just going to write SD, 1 standard deviation above average. Right here is 2 standard deviations above average. And then we've got 3 standard deviations above. So that's what I would do. I wouldn't even do the X bar plus the sigmas. And then I would jot down, this is 1 standard deviation below. and then 2 standard deviations below, and then 3 standard deviations below. And it's possible to be more standard deviations above and below, but most of the population, 99.7% of the population, you can see down here, is between 3 above and below, within 3 standard deviations of average. So we don't write any more because it's just such a small percentage of the population. So these percentages are helpful because this helps us decide how many data values are within certain ranges. So 99.7% are within 3, and then 95% of the data is within 2 standard deviations away from mean, and then 68% are within 1 standard deviation away from mean. And this helps us decide how sort of common or normal is a certain data value. And I think I gave the example in my last video of this former student that I had whose son took the ACT, and she was really concerned because she thought he did poorly. And then after she told me his score, I looked up the standard deviation, and together we looked at this chart and realized that he was, more than 2 standard deviations above average. And what I did is I showed her these percentages, and I said, if you look at these percentages, 2.5% of the population is scoring above 2%. So that means your son is in that 2.5% of the population that is scoring that high. And when I put it that way, she's really able to see how well her son did. But without this sort of picture, it was kind of hard to know when you can't compare to the whole population. So these percentages here in the chart give you the percent of the population in general that's in between these standard deviations. So again, this is a chart you might want to copy down in your notebook or something so you can refer to it, because you're going to need it quite a bit in the homework. So let's go ahead and do some examples. And these examples, we're going to use this chart above in these examples. So for example 4, it says for 2015 high school graduates, the mean SAT math score was 515. So I'm just going to write down mean is 515, and then the standard deviation was 116. In a typical class of 450 students, so I'm just going to write n equals 450 because that's the total number of students, what percent of students scored between 631 and 747? So in a problem like this, what I would do is I would first draw the normal curve. And for the problem, actually, I should have added in this problem, the SAT scores are normally distributed, because that would tell you that you can go ahead and draw the normal curve. But let's just assume they're normally distributed. You draw a bell curve and draw a vertical line down the middle, and the mean always goes in the center. So you look in the problem and you find the mean. It should be given in the problem. In this case, it's 515, and you write it right in the center. And then what I would do is I would draw 3 vertical lines on the left, 3 vertical lines on the right. And these represent 1 standard deviation above, and I'm just going to write a +1. And then a +2 and a +3 and a -1 and a -2 and a -3. If you want to write 1 above, 2 above, 3 above, and 1 below, 2 below, 3 below, you can do that as well. And then I could write a 0 in the middle. That sort of represents the 515 because that's in the center. So then what I do is, seeing as how it's asking me, it wants to know the percent between 631 and 747, I need to figure out what values are at all of these standard deviations. So that's the thing that I'm going to do next. And to do that, what I'm going to do is I don't use plus and minus 1, 2, and 3. You have to use the standard deviation that was given in the problem. That's important. So you start with the mean, 515, and then what you're going to do is you're going to add 116 to get to the next number. So when you add 116 there, you end up getting 631. And then you add another 116. Whoops. 116, and then you get 747. And then right there, actually, I could stop because I see the 747 in the problem, but it's not a bad idea to keep going because there is a part 2 here. So just to be thorough, I'll add again and I get 863. And then what I do to go to the opposite direction is I subtract 116. So I'm going to do 515, whoopsies. My eraser is not the easiest to use. Okay, so I'm going to subtract 116 and I get 399, and then I do it again, minus 116, and I get 283, and then I do it again, minus 116, and I get 167. So the way that you read this is these are all scores, like the whole bottom, these are scores, SAT scores. So if, for instance, let's say I scored a 167, I would look at this chart and see, oh, I was 3 standard deviations below average. That's really, really rare and not a good way. It means that I didn't do well. So in this case, we want to know how many scored between 631, which is right here, and 747. So it's this area, shaded area. And if we look, it's 1 standard deviation above to 2 standard deviations above. So you go up on the chart here and you find where is 1 standard deviation above, where is 2, and that's this area right here. And it shows that it's 13.5%. So the answer is 13.55%. So you have to use the graph above in order to get the answer for this problem. And then for the next part, so I'm just going to scroll down. Looks like we're kind of running out of room here. I would actually, I'm just going to use the graph above. You might want to draw a separate graph on your paper. So this is where I would pause the video and draw a normal curve. And I draw the mean in the middle, and I just redraw this entire picture with all of the SAT scores on the bottom. And then I'm just going to use my eraser here so we can save a little time. There we go. Okay, and then I've got 747. Okay, and so I'm going to go ahead and use, for this next problem, I'm going to redo this. So in this one, I went less than 283. So here's 283, and I'm going to, less than is everything to the left. And then I don't stop at that standard deviation line of 3, I keep going. And then greater than 747, I shade everything to the right of 747 there. And this is where, so I do the same thing, whoops, sorry about that. I do the same thing I did above, and I go up into my graph and I try to look at the numbers. It looks like I'm pulling out between 2 and 3 and then after 3. So it looks like between, here's 2 below and 3 below. So it looks like those numbers, oops, I just drew over that. It looks like I want 2.35 and 0.15. So it looks like this right here is 2.35%, and this area is 0.15%. And then on the right side, it looks like they're the same. So 2.35% and 0.15%. And so if I add all of those numbers up, then I'll get the total percentage. So if I add 0.15% plus 2.35%, which is 2.5, and then another 2.35 on the right, and then another 0.15, we end up getting 5%. So 5% of people scored less than 283 or greater than 747. And I should have mentioned this at the very beginning, that the percentage under the entire curve is 100%. So underneath the whole curve is 100. The other thing that you can think about that might also be helpful is if the whole thing underneath the whole curve is 100, each half is 50. So that's another characteristic that's helpful to know. The other thing that we could have done, if we didn't want to add up all of those, we could have looked up here and seen that 95% are between 2 standard deviations from average. So if we know that this is 95%, then the other part must be 5. So that's another way to go about these problems. A lot of times there's more than one way. And so I would just, do whatever way makes more sense to you. Okay, so one problem with the problem that we just did, or potential problem, is the nice thing about the problem that we just did is the values that we were asked about in the problem were exactly on the standard deviation line. So actually, let me just scroll up real quick. So we were asked, for instance, about less than 283. Well, that score just happened to be on that exact standard deviation line of 2. So did 747. Well, what if you want to know information about a score that's not? Like, let's say I scored 520 on the SAT. That puts me like right here. Maybe I want to know how I stack up. What's my standard deviation? It's between 0 and 1, but maybe I want to know that exact number. And that's what a z-score is. So a z-score is a measure of position. It tells you how many standard deviations the value is above or below the mean. So it's just a standard deviation, fancy name for standard deviation. So let's scroll here. And let's do an example. So for example, the mean height for women is 65 inches with a standard deviation of 3.5. I am 5'4", which is the same thing as 64 inches. So how many standard deviations away from the mean am I? So just looking at these, if I'm 5'4", 64 inches, and the average height for women is 65, I'm below average. So just based on that, I can expect that my standard deviation should be negative, because negative means you're below average or to the left of the mean on the number line. But I could find my exact z-score. So what I could do is I could use that formula above. I could do the data value minus the mean divided by the standard deviation. The data value is the value given in the problem that's for the specific person or what you're studying. So in that case, that would be my height. So what I'm going to do is I'm going to take 64 inches minus the mean, which is 65, divided by the standard deviation, which is 3.5. And if I do that, I get negative 0.286, which is I would say slightly below average. And the reason it's slightly is because it's 0.286. It's not even one standard deviation below average. So I'm really, really close to average, which you could probably have told me that just looking at my height. But this just puts a number to this. And to give you a real life example, so my daughter, who's 18 months at the time that I'm making this video, she had heart surgery when she was born. And there were several times when they gave us z-scores for how narrow her arteries were. And it allowed us to decide, or to determine, the doctors to determine how normal or abnormal it was. So after they did her heart surgery, they gave us a z-score. I think it was I know it was negative, but it was a small decimal. It was like 0.05 or something like that, negative 0.05. And the doctor said, well, it's a little bit narrower than normal, but and my husband asked, what's the z-score? Well, they gave us the z-score and we said, oh, wow. So it's really, really close to average because it's such a small decimal. It's so close to that 0, which represents the mean. And this put us at ease and allowed us to just, be at peace knowing that it was really close to average, other than just hearing, oh, it's below or narrow. So that's just another real life example. So for example 5, this would be a great place to pause the video and try this one on your own. And I'm going to go ahead and walk through it. So we've got 2 students here, and we want to find the z-score for somebody that scored 760 on the SAT and somebody that scored 480. So we're given the mean, 515, standard deviation, and we want to do the z-score for both of these scores. So I'm just going to put a line down the middle. I'm going to do 2 separate problems. So we're going to do 760 first, and then we'll do 480. So for 760, they scored above average, so you should hopefully expect a positive result here. So we're going to do the data value, 760, minus the mean, divided by the standard deviation, and we end up getting 2.112. So we've got above average because it's positive. And I would say it's quite a bit above average, so they did really well, because 2 standard deviations above average. I mean, if you think about that chart with the percentages, we said that 95% of people scored between 2 standard deviations away from the mean. So that means if they scored above 2, that means they're over here. So they're scoring better than, more than 95% of the population. So for the score 480, we're going to take that score minus 515 divided by 116, and you're getting negative 0.302. So it's negative, so that means it's below average. A 0.302 is between 0 and negative 1. So I would say it's below average, but it's still, I would say, pretty normal. So that person, just to give you an idea, if this is 0 right here, they're like right there. So negative 0.302, whereas the other person is over here. So they're a lot farther away from the average. Okay, so let's talk about a rare event, and this relates to what we were just talking about with the person that got the 760. So we say a rare event is when a measurement is more than 2 standard deviations away from the mean. So based on that, it says, are either the scores from example 4 considered rare? And we would say yes, 760 is rare because it's 2.112 standard deviations away from average. We could even say, instead of away, we could even use the word above. That's a little bit more specific. So there's one more thing we need to talk about here, just another way of comparing values with others. And this one I would say is really applicable to our lives, and that's percentiles. So this is much more common, I think, than standard deviation. So an example of percentiles, a lot of times you see percentiles, at the doctor's office. So if you have kids, you probably heard this, or maybe you remember going to the doctor when you were young. And usually they tell you, you have a certain percentile for height and weight. So for example, let's say my daughter is in the 60th percentile for height. That means she is taller than 60% of the population, and she's shorter than 40. So whatever your percentile is, your percentile is the percent of people, we can say either below is one way to describe it, or less than you. So it's always talking about the below. Another example, so Sam scored in the 25th percentile on the SAT. He scored better than 25% of the population, and he scored worse than 75. So if this is Sam, 25% scored less than him, 75% scored better. And in terms of tests, if you have a percentile, that's not your actual score. I went through this recently with my daughter because she got some standardized test results back, and she ended up scoring in the 80th percentile, and she was bummed because she thought that meant that she scored around the 80% for the test, and she wanted to do better. But I actually explained in her case, so this is, let's say this is my daughter, it means that she scored better than 80% of other kids her age. 20% scored above her. So does that mean that she scored an 80% on the test? No, it really just shows how does she compare with other children. So in some cases, in some standardized tests, I've seen even like the kindergarten one, for example, when they the kids take the kindergarten NWEA, they can get a pretty low score and still score in the high percentile, because those kids, the way they do the test, they set the test up where the kids don't score super high because they're not used to taking a test on a computer when they're 5 and 6. But if they score better than most kids, then they can still have a really high percentile. So just a really simpler way than standard deviation to compare somebody with the entire population. So that's it for 7.3. As usual, let me know if you have any questions.